So we've been talking about vapor pressure, and now we're going to talk about a couple of the other consequences of vapor pressure and the concept of boiling and critical temperature and pressure. So we understand the concept of that vapor pressure, at any particular temperature, all liquids have a certain, amount of their gas above them because it vaporizes. But if we actually increase the temperature to a certain point, we get to where the vapor pressure is actually equal to the total pressure sort of above the solution. And what happens is the solution is essentially vaporizing at an incredibly fast pace, and we associate that with the process of boiling. That's that the bubbles are actually forming sort of like inside the solution. The molecules have so much kinetic energy that they can actually form those gas molecules. They don't even have to wait to be at the surface of the solution to jump out. They can actually form in that solution. So you can think of boiling simply as, evaporation on steroids. Technically, it's the temperature at which the vapor pressure is equal to the total ambient pressure above the liquid. So, sort of a practical example is that water boils at about 100 degrees Celsius in Michigan because our atmospheric pressure is relatively close to 1 atmosphere. But it boils at about 91 degrees in the state of Wyoming because they're at 6,000 feet. So the ambient pressure, pressure out here in Michigan is about 1 bar, maybe 0.97 bar, and the pressure in Wyoming is closer to like 0.8 bar. So that's why the boiling point of water is so much less in the state of Wyoming. Now we'll define something as the normal boiling point is the temperature at which the liquid boils at 1 bar pressure. Now, the temperature at which, or the vapor pressure of a particular solution, we know that that is a function of temperature, and it's also a function of the enthalpy of vaporization. So remember, delta H of vaporization is basically how much energy it takes to go from the liquid phase up to the gas phase. And so here is an equation that allows us to relate vapor pressure of a particular solution at two different temperatures. So T1 and T2 are the different temperatures, and obviously the temperatures need to be in units of Kelvin because we're talking about gases. We're using the gas constant R, and the vapor pressure is P1 and P2. So pressure at T1 and T2 respectively. Now, a couple of nuances about this equation in that the units, again, are kind of important. So we know that T1 and T2 are going to have to be an absolute temperature scale. The vapor pressure, P1 and P2, doesn't matter what those units are as long as they cancel out, and we're taking the natural log of it. And the enthalpy of vaporization is usually in kilojoules per mole. And so again, in this case, we would use the R value of 8.314 joules per Kelvin mole. And so our moles be there, there's our kilojoules, and then there's our Kelvin in our temperature scale. And of course, on the left-hand side, there is no units because whatever the pressure units are, they cancel out, take the ln, no muss, no fuss. So a hypothetical question, if we have a solution that has an enthalpy of vaporization of 38.7 kilojoules per mole and a normal boiling point of 110 degrees Celsius, what is the vapor pressure at 97 degrees? So in this case, it's really just sort of algebra, right? We know we have the enthalpy of vaporization, so we know delta H of vaporization. We know R. We know T1 and T2, so 110 degrees, 97 degrees. And we are being asked for P2, and we're not actually given a P1, but right there we do. We're not given a P1 because we don't need it, or we're sort of told what it is. We're told that the normal boiling point is 110 degrees Celsius. And remember, normal boiling point is the temperature at which the liquid boils at one bar pressure, which means the vapor pressure is 1 bar. So what does that all mean? Well, that means that the vapor pressure of this solution at 110 degrees Celsius is 1 bar pressure. That's the definition of normal boiling point. So from there, it's just plugging and chugging, And if you actually go through and do the math, you calculate a pressure of 489 torr. Remember, 1 bar pressure is 750 torr. So this makes sense in that we would expect the vapor pressure, if the normal boiling point is 110 degrees Celsius, that's 1 bar, that's 750 torr, we would expect the vapor pressure at 97 to be less than that, and in fact it is. Now, Raoult's law is sort of an extension of solutions about what happens when we add solute to a solution. So remember, a solution is some homogeneous mixture where we have solute dissolved into some solvent. So imagine, if you will, I have some sugar water. So in the case of if I had some sugar water, that means, if we remember about what vapor pressure is coming about, it's basically the molecules at the surface of the solution having enough energy to sort of jump ship and go up into the gas phase. Well, if I have a sugar molecules evenly distributed, those sugar molecules are going to physically be in the way of the molecules on the surface. So basically, you can almost think that they're taking up those spots, that are the exit point of the solution. So a vapor pressure of the solution, and these are referring to vapor pressure of the solution is always going to be less than that of the pure solvent, because as I add solute, the solution will have, less sort of exposed molecules, if you will, so the vapor pressure will go down. So the vapor pressure of the pure solvent is always highest as I put more stuff in it, more stuff in the way. And we're going to spend a lot of time in further chapters talking about this. And it turns out the equation, there's an equation for that. It's called Raoult's law. It says the vapor pressure of the pure solvent times the mole fraction of the solvent is equal to the vapor pressure of the solution. Now notice that this is mole fraction of the solvent. So if it's a pure solvent, then mole fraction would be equal to 1, and so the pressure of that solution, even though it's not, is the same as the vapor pressure of the pure solvent. So as the concentration, as measured by mole fraction of the solvent, goes down, so does the vapor pressure. And that's a relatively simple equation, so we're not even going to spend time sort of going through that. Although there is an equation here calculating the vapor pressure of a solution of water at 100 degrees Celsius, 30 grams of glucose dissolved in 200 grams. And sort of simple algebra, knowing Raoult's law, I'm going to calculate the mole fraction of the solvent. So this is a solution, so we need to know the number of moles of the glucose and the number of moles of the water. And it's relatively straightforward. Okay, so what happens if we heat a solution, we heat a liquid, we know that the vapor pressure goes up. All right, so a different case is what happens if we have a closed container. Right, so I have my closed water bottle, if you will. And so as I heat that closed container, the temperature will go up. So since the temperature goes up, more boils, or not necessarily boils, it more evaporates. And so the vapor pressure, because the vapor pressure is tied to temperature, so more of the liquid goes into the gas phase. But then we have more in the gas phase. Since it's in a closed container, that more gas means that the pressure above the solution is greater. So that means the boiling point of the solution is increasing, which means that the boiling point goes up. And so the boiling point goes up, the temperature goes up, more liquid is going into the gas phase. I have more gas, the vapor pressure is going up, and eventually get to the point where I have this liquid, I have the gas that is so concentrated, the pressure is so concentrated with whatever the liquid was, that it's really hard to even think about where the fact that gas ends and the liquid begins. And the easiest way to sort of like think about it is it's sort of like a cloud or a fog, right? Fog is not a case of this, but it sort of looks like that it's a liquid and a gas sort of all at the same time. It has the solvent properties of a liquid, but it has the fluid properties and the expansion properties of a gas. So the temperature at which this sort of like ambiguity between the gas and liquid is known as the critical temperature, and then there is an associated critical pressure associated with that, the pressure basically which that the gas creates that mass. In the case of water, the critical temperature and critical pressure is 647 Kelvin, which is not an unreasonable temperature, but the critical pressure is 218 bar. So making a what is called a supercritical solution, supercritical fluid, is difficult for water, right? So if you can get above that temperature and that pressure, you reach the supercritical, and then of course you have, that sort of like foggy type thing. You got weird chemistry because the supercritical fluid has the solvent properties of a liquid, but it also has the compressibility properties of a gas. And there's actually quite a few practical applications for supercritical fluids. The most notable is supercritical carbon dioxide is actually used for decaffeinating coffee and for dry cleaning. So that strange chemistry of, is it a liquid, is it a gas? Well, it's yes is kind of the answer. Has some practical applications. Good luck.